Welcome to our next video on Lewis structures. In this video we're looking at exceptions to the octet rule. We've already seen hydrogen be an exception to the octet rule, but here we're going to look at some more elements in special situations that can be exceptions to that octet rule. Again, this video follows along with that Word document that has those instructions on how to complete writing Lewis structures. So you should be following along with that while you're watching this video. So the first case we're looking at for these exceptions to the octet rule are other things like hydrogen that can have deficient octets. So these would be things that have less than 8 electrons around them. So here we've already seen hydrogen be an example. Here we need to look at a couple other examples for these. You don't run across these too often, but just often enough where you need to see what to do with that. So for our example we want to do is I'm going to do BeH2 as our example. So for BeH2, you still follow along the same set of steps, the same sequence of things that we've been doing for any other Lewis structure. We need to figure out how many valence electrons we're actually dealing with. Beryllium lives in group 2A, so that's going to be 2 valence electrons. Hydrogen in group 1A for a total of 4. So right away you're going to see we're going to have a trouble dealing with the octet with only 4 electrons. But continuing, we're going to pick out the central atom. Usually it's the first one listed. Remember that hydrogen cannot be the central atom, so we're definitely looking at beryllium being our central atom. Hydrogen is going to be the outer atoms. We need a single bond connecting each outer atom with that central atom. Now normally we would next complete an octet of electrons around each outer atom, but as we saw before, hydrogen doesn't get an octet. It's not going to get any lone pairs. So now we're going to check and see how we've done. We need 4 electrons. Do we have 4 electrons? 2, 4. We have 4 electrons. We know hydrogen doesn't follow the octet rule. It follows the duet rule, and it has its 2. This hydrogen has its 2. But what about the beryllium? Beryllium ends up with 2, 4. We have a deficient octet. We have less than 8 electrons around beryllium. So there's going to be cases where you're going to have less than 8 around a certain atom. Usually those elements are going to exist in either group 1A, 2A, or 3A. And the reason why they're going to come from those groups is those groups are not contributing a lot of valence electrons to begin with. Beryllium's only contributing 2 valence electrons. It's not contributing a lot to begin with. That means those elements in group 1A, 2A, and 3A are not contributing a lot of electrons. They're going to end up having deficient octets, or at least capable of having deficient octets. So if you have a deficient octet, less than 8 electrons, what you want to do is you want to stop and say, hey, does this element appear in groups 1A, 2A, or 3A? Because those are going to be the groups that have the potential. Doesn't mean they have to. A lot of times they may still follow the octet. But those 3 groups, 1A, 2A, and 3A, are going to be those things that have the potential to have those deficient octets. Those having less than 8 total electrons here. Beryllium's in group 2A, so that kind of makes sense for that. You don't run across these deficient octets too often, but just often enough that you want to make sure you're comfortable in dealing with those. So that's the first class, or the first category of kind of not following the octet rule, having those deficient octets. The next category are the category that have an odd number of electrons. What you've probably noticed so far is in every single Lewis structure that we've written so far, in all of our videos, you've seen an even number of electrons. And that's because molecules with an even number of electrons tend to be the most stable. When you have an odd number of electrons, those molecules tend not to be as stable. So we don't have a lot of examples of that, but there are some odd number of electron molecules that are common that we want to make sure we're able to deal with scenarios where we have an odd number of electrons. So our example for an odd number of electrons would be something like NO2. Not nitrite ion, NO2. Nitrogen dioxide. This is a gas. So when we write out this Lewis structure, we'd write this out the same way we would start anything else. Nitrogen's in group 5A for 5 valence electrons. Oxygen's in group 6A for 6. We see we have 17 electrons, an odd number. I would say, being these odd number of electrons are so rare, anytime you get an odd total, double check your math just to make sure you are dealing with an odd situation or an odd number of electron situation, as opposed to just miscounting either the addition or how many of each thing you have, or if you're looking at maybe things in the wrong group number. Check out those things first, because you don't find these odd number of electrons very often. Now, these odd number of electron molecules are really a subclass of what we just did, the deficient octets. I'm going to give them their own category, though, because of the way you deal with them. You deal with them in a very different way than how you deal with kind of some of the other deficient octets or expanded octets that we'll talk about in a little bit. So the easiest way to deal with an odd number, and it's going to sound weird when we first start this, but it ends up getting you to the right spot at the end, is whenever you have an odd number of electrons, and you've checked that you really truly do have an odd number, what you have to do, it sounds very weird, you have to imagine an extra electron in there. Don't worry, we'll deal with that later at the end, but for the time being, you're going to imagine that you have an extra electron in there. So for right now, we're going to go under the pretense that we're actually dealing with 18 instead of 17. Once you've imagined that extra electron, you just go about the process the same way you would for anything else. Pick out that central atom. Well, here we're going to be looking at the nitrogen as the central atom, first one listed. That's going to make the oxygens the outer atoms. I need a single bond connecting each outer atom with the central atom. Next, you would complete an octet around each outer atom by making 3 lone pairs, just like we've done many, many other times. Next, you check and see how you've done. We're looking at 18 electrons. Do we have 18? 2, 4, 6, 8, 10, 12, 14, 16. I don't have those 18 electrons. Where do I need to put those extra electrons in there? Well, those are going to go in as a lone pair on that central atom. So now we're going to redo our checks. 2, 4, 6, 8, 10, 12, 14, 16, 18. That matches. Now we're going to check our octets. Oxygen on the left, 2, 4, 6, 8. This oxygen, 2, 4, 6, 8. Nitrogen, 2, 4, 6. We don't have an octet on nitrogen. Here, we have the correct whole number. We have 18, but they're not arranged properly. Remember how we deal with that rearranging of the electrons. We pick an outer atom, and we take the lone pair from that outer atom and make a multiple bond. Make an extra bond. It doesn't matter which oxygen you pick or which electrons you pick. This molecule is another example of something that has resonance. I'd get a different resonance structure if I picked the other oxygen to share with. Here we're not going to focus on the resonance portion of this. We're just going to focus on dealing with the odd number of electrons. But this is another molecule that does have resonance structures. If I draw the result of that, I would get this structure here. Go through and do your checks. 2, 4, 6, 8, 10, 12, 14, 16, 18. I have 18. Check your octets. Oxygen on the left, 2, 4, 6, 8. Oxygen on the right, 2, 4, 6, 8. Nitrogen, 2, 4, 6, 8. This looks good. But here's where you got to remember something. Remember, I didn't really actually have 18 electrons. I actually have 17. I had to imagine an extra electron. I hallucinated an extra electron to go through the normal process. Well, one of these electrons doesn't really exist. So anything you imagine, you need to unimagine that thing. Same way as if you had an imaginary friend when you were a little kid, chances are you don't have that imaginary friend anymore. You unimagine that imaginary friend. I really need 17 electrons, not 18. So one of these electrons doesn't exist. The electron that doesn't exist is one of these that are on the lone pair of that central atom. So this is the one time when we're not going to have electrons paired. Every single Lewis structure and every single set of electrons you've dealt with so far have had these be paired. One of these doesn't exist, so that's the one I'm going to remove. I'm going to remove one of these electrons. I'm only going to have a single electron on that central atom unpaired. So now let me go through our checks. 17 electrons, 2, 4, 6, 8, 9, 11, 13, 15, 17. I have my 17. Check the octets. Oxygen on the left, 2, 4, 6, 8. Oxygen on the right, 2, 4, 6, 8. Nitrogen, 2, 4, 6, 7. So this is what I mean when I say this is a special type of a deficient octet. I do have less than 8, but the key feature in this is not the less than 8, but the odd number. So this is how you deal with an odd number of electrons. Even though it seems kind of weird, some of you are probably looking at this and saying, man, why am I going through the hassle of imagining an electron and then unimagining it later? Well, because if you do this process, you're going to get the correct Lewis structure. Even though it seems weird, it's a guaranteed way of making sure you get the correct Lewis structure coming out at the end. That's why everyone uses this technique, even though it sounds strange to imagine something that doesn't exist, just to take it away later. So you don't run across these odd number of electrons too terribly often, but every once in a while you run across something that has an odd number of electrons. This is how you do it. Imagine that extra electron and then later unimagine it, and the one that gets removed is from the lone pair on that central atom. So that's how you deal with odd numbers of electrons. That's a special case, that's why I gave it its own category. That's the second kind of exception to the octet rule. The third exception to the octet rule is the expanded octets. So these are going to be elements that have more than 8 electrons around them. We're going to do several examples of these because these are actually fairly common. You run across these all the time. These are not altogether that rare like these first two categories that we just talked about. But first, a little bit about the criteria for having these expanded octets. We're going to look at this criteria as we go through some specific examples. The first criteria that was listed was must be in the third period or below. Well, we haven't talked a lot about periods. Remember, periods are the rows on the periodic table, not the vertical columns, not the groups, but the rows. The element has to be in the third period or below. Let's think about what's special about that third period. Well, in that third period, you're in the third energy level. In that third energy level, what you have available are d orbitals. Those d orbitals don't kick in until you're in the third energy level. And now you're starting to see how some of this octet rule comes in. If you think about how many electrons can fit in a p orbital, you know there's 6. If you think about how many fit in an s orbital, there's 2. How many electrons does that give you? 8. That's a little bit of where this octet rule comes from, of how many electrons can be around something. Well, now, if we're in the third period, what do we also have? We also have d orbitals that are available. So that means I can go beyond potentially these 8 electrons. And I want you to kind of look at this and do this with an actual electron configuration. We look at the electron configuration for sulfur. 1s2, 2s2, 2p6, 3s2, 3p4. You may look at sulfur, and sulfur's in the 3rd period. Now I'm telling you that, hey, we can have an expanded octet on sulfur because of d orbitals. But you don't see any d orbitals here. Well, they're there. It's just not filled. Just because there's no electrons in there doesn't mean they're not available. Right now, as you're watching this, theoretically, no one's in your car right now. Just because no one's in your car right now doesn't mean it ceases to exist. It's just unoccupied at the moment. Sulfur has d orbitals available. Anytime you're in the 3rd energy level, d orbitals are possible. D orbitals can exist. They're just not being utilized at the moment. So that's what makes the 3rd period and below special for having these expanded octets. For the other 2 criteria, we're going to look at that with some specific examples that we kind of want to go through and do. The first example I want to do is SF6, sulfur hexafluoride. We're going to go through 1 sulfur, 6 total fluorines. Sulfur is in group 6A. Fluorine is in group 7A. When we total up everything together, we're looking at a total of 48 electrons. So we got a lot of electrons we're putting in here. Determine the central atom. Central atom's usually the first one listed. All of your other atoms are going to be the outer atoms. So I'm going to stick 6 fluorines around this central sulfur. I'm going to make a single bond connecting each outer atom with the central atom. The next step when you're doing a Lewis structure is to complete the octet on those outer atoms. So for these outer atoms, we need 3 lone pairs on each, just like what we've been doing. So I'm going to fill in 3 lone pairs on each one of these outer atoms. Next up, it says check to see how you've done. You should be looking at 48 total electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. We have our 48 electrons. We also need octets around things. Let's check the outer atoms. Each fluorine, as you go through, will have 2, 4, 6, 8. That fluorine will have 8, 8, 8, 8, 8, 8. All the fluorines will have their 8. But the sulfur, when you look at the sulfur, will have 2, 4, 6, 8, 10, 12. So it looks like we have an expanded octet. Anytime you draw an expanded octet, I want you going through this 3-step sequence of criteria. First, is your expanded octet on a 3rd period element or below? That's the only chance you have of an expanded octet. Sulfur is in the 3rd period, so that's okay. Next, it must be on the central atom. Look at that set of criteria again. It must be on the central atom. You're not going to have expanded octets on the outer atoms. It's got to be on the central atom. Here, sulfur is on that central atom. So that's okay. 3rd criteria is it has to be necessary. Just because you can do something doesn't mean you should do that. If there's a way to write this where you do not have an expanded octet, you should go that route and not expand the octet. But here, I very clearly have 6 things bonded to this sulfur. The only way I'm going to get 6 things bonded to the sulfur is if each bond has 2 electrons, I'm going to be over 8 electrons real quickly. There's no other way I could have this molecule be except having that expanded octet on the sulfur. So this example meets all of those criteria. Expanded octet on a third period element or below. It's the central atom, and there's actual necessity. I just didn't do it just because. I did it because there was really no other way. Now we're going to look at a couple other examples of kind of using these criteria, because these expanded octets are actually quite common. You see these fairly often. The next molecule I want to do is also an expanded octet. This one would be SF4. So here I would have 1 sulfur, 4 fluorines. Sulfur's in group 6A, fluorine's still in group 7A. Here I'm looking at a total of 34 valence electrons I need to deal with. I still start this off the same way I've done everything else. Pick out the central atom, usually it's the first one listed. Then you're looking at the outer atoms. Make a single bond connecting each outer atom with that central atom. Next, complete an octet around those outer atoms. So I'm going to make 3 lone pairs around each one of these outer atoms. Check and see how you've done. I'm looking at 34 electrons that I need. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I'm short 2 electrons. Well, I need to get 2 more electrons in the molecule. Where will they go? Well, that's when we start making lone pairs on that central atom. So now, if I recount, I will have 34. But I never check the octets. I should go back and check the octets. Each of the fluorines will have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Sulfur, 2, 4, 6, 8, 10. So I drew this as an expanded octet on sulfur. Anytime you draw an expanded octet, go through this set of criteria to make sure that it's okay that you have an expanded octet. First criteria you want to go through is third period or below. If it's not in the third period or below, there is 0 chance of an expanded octet. So you better check that first. Sulfur is in the third period, so that's okay. Next, you're only going to expand the octet on the central atom. Sulfur is the central atom, so that's good. The third criteria is it necessary? Well, let's kind of go through here and see if it's necessary. Is there another way I could have drawn the molecule in a way where I did not expand the octet if I actually followed the octet rule? Well, to check that out, let's go back to when we were here, because those were the 2 electrons that really broke the octet on this. Well, were there any other choices of where I could get those 2 extra electrons in? And you see very quickly that anywhere else I would put those electrons would not make things any better. It would actually make things worse. If instead of putting them on the sulfur, I put them as another bond between the sulfur and the fluorine, well, here, this is actually worse than what I started with as well. Because here, I still have an expanded octet on sulfur, 2, 4, 6, 8, 10. And now I have 2, 4, 6, 8, 10. Now I have an expanded octet on fluorine, which can't have an expanded octet because it's not in the third period and it's an outer atom. So that would actually make things worse instead of better. So let's get rid of that. What other options would I have? Well, could I add even more lone pairs on the outer atom? Well, is that an option? Let's actually show that in a different color. Is that an option? Does that make things better or worse? Well, yeah, it fixes things on the sulfur, but it really messes things up on the fluorine. 2, 4, 6, 8, 10. Now I have 10 around the fluorine, which can't handle it because it's not in the third period or below, and it's an outer atom. That's going to make things worse. So the only place those extra electrons would go could be as a lone pair on that central atom. There was necessity in order to do that. I didn't do it just because. It's because it was necessary. Any other option would have made things worse instead of better. So this fits all three of the criteria we need in order to have an expanded octet. Third period or below, central atom, and we demonstrated that it was necessary. So here's going to be our correct structure. I want to do one more example with these expanded octets. And for this one, I'm going to use this molecule, SF2. Now, before we do this one, I'm going to kind of skip ahead a little bit. If you follow my set of instructions for how to write Lewis structures, this one wouldn't come about. But some other techniques, you might accidentally write something that is incorrect here. So, sulfur's in group 6A, fluorine's still in group 7A for 20. So I'm not going to do this stepwise, because if we use my technique, you'd never be at that necessary clause. You'd get the right structure regardless. But if you use some other techniques, what if you accidentally got to this structure? So let's imagine you wrote out this structure for this. And you go through and you count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That looks good. Now again, can't stress this enough. If you use the set of directions I've laid out for you, you'll never get to this structure. Which is going to be good because this is the incorrect structure. But other techniques could lead you to this structure. So let's head 20. Check out the octets. 2, 4, 6, 8. Yes. 2, 4, 6, 8. Yes. Sulfur. 2, 4, 6, 8, 10, 12. So here, you'd go through that set of criteria and say, I have an expanded octet, is it okay? Well, sulfur's in the third period, so that's okay. Central atom, that's okay. Here's where this fails. And this fails the necessity clause. I can't do it just because I'm allowed to. There has to be a real reason to do this. This is not going to be our correct Lewis structure, because there's a way of drawing this molecule where we don't have to have an expanded octet. And this would be the one we would do if we followed the technique where I laid out. If we follow the set of instructions I gave to you, you would never have this top option as an even possibility to consider. But other techniques might give that to you, that you'd then have to refute with the necessity clause on this. So if we go about the way I did things with you, you would determine the central atom, make a single bond connecting each outer atom with the central atom, then you would complete octets on these outer atoms. You check and see how you did. 2, 4, 6, 8, 10, 12, 14, 16. I'm short 4 electrons. Where would they go? 2 lone pairs on that central atom. You check and see how you did. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. That's good. You would check the octet rule. 2, 4, 6, 8. 2, 4, 6, 8. Both fluorines are good. The sulfur, 2, 4, 6, 8. Here, even though sulfur is capable of expanding the octet rule, I should not expand the octet on the sulfur. I should not write this top structure because there's no reason to expand the octet. I can correctly draw this while still following the octet. So I just wanted to show you that necessity clause, that just because you can do something doesn't mean you necessarily should do it. Just because sulfur is capable of expanding an octet doesn't mean you should automatically expand it. You should only do that if there's good reason to. And the top, there's no good reason to when you compare it to what you could write on the bottom. So that's our video on different exceptions to the octet rule. We have the deficient octets. Remember, those can come up when you have something group 1A, 2A, or 3A. There's the odd number of electrons, where you're imagining that extra electron. And then finally, we dealt with the case where we have expanded octets. go through the set of criteria, you're going to see these expanded octets quite a bit.